Introduction to calculus is about relationships between two variables, right? So what we're going to look at is a bit more in-depth about how one changes with respect to another. So looking at the first exercise examples quickly, what it shows you is a few different 2D shapes. If you were to fill these up with water, all right, and just have a graph showing you the time it takes to fill it up at a constant rate, so it means you're not changing how much water is going in at a time, it's the same rate, but the actual height of the water in the object, right? For the first one, because it's a block, so as you fill it up, the height will just be constant, so that what you would get is the constant bit. But when it goes narrow, obviously if you're still putting the same amount of water in, because it's a lot smaller space, it will go a lot faster, right? Then something that's getting narrower and narrower as you go, obviously with the water going in, the amount or the height of the water or the depth would actually increase as you go over time, right? So that's what this one's showing. This one at the start, because it is getting wider, so the water goes in, or the height is slower, but then as the width of the object narrows, then the height goes a little bit faster. Okay, just being able to understand, think about in terms of how does the depth of the water change over the time, provided that the amount of water that you're pouring into each object is constant. Okay. This one, now, this is more of a physics type sense, but what it does show you is if you think it's not actually a two-dimensional drawing. It's essentially just a particle as it starts from a point on a straight line somewhere, right? And it's just moving back and forth. Now, for mathematics and for physics for that matter, we treat the direction to the right as being positive, direction to the left as being negative. So what this simply shows, it's not a 2D graph. It's just where is it relative to the starting point, all right, at a certain point in time. Okay? So what this means that it starts 5 meters to the right. So if it was drawn to scale, if this was a 0 point, it would probably be over here somewhere. Okay? Then this bit means that it's traveling to the right again, even further away, to the 10-meter mark. Right? This part here means that for those 4 minutes, from the 3-minute mark to the 7-minute mark, the particle is actually stopped. Right? So it's stopped there, and it's just waiting, chilling. Then this part means that it's actually going back, and because it's a little bit steeper, it's going fast at the start of it, and then it slows down as it gets towards the origin. When it hits the x-axis, that usually means it's returned to the 0 point. Hopefully that makes sense. Going. Right. The next example just shows you what's happening. Again, think left and right. Going to the right is a positive direction, going to the left is a negative direction. So this point here, you can think of it as it started over to the left side of the origin, it's gone past it and keeps on going. Alright? This point here momentarily stops and then it's now going back towards the origin. So going from there to there, now it's going back, and then it's going to go forward away from it again. Constant rate of change. So what it means is this phrase here, what one variable, or what happens to one variable as it changes with respect to another. You could say that if you traveled the 100-meter sprint, right? The Olympics now is on. 100-meter sprint, someone that's very, very fast would do it in less than 10 seconds, which actually means they cover 100 meters in less than 10 seconds, which is, if you simplify that, every second they're covering 10 meters. Of course, that's on an average because at the start of it they speed up and at the end of it they go a bit faster kind of thing, right? If someone slower, like me, was to do it, and I took a solid 15 seconds or something, right? Whatever that works out to be, it's about 6 point something. Okay, that means I'm actually only covering 6 meters every second, right? Whereas the other person will be covering 10 meters every second. So with this, it just means that the entire 100 meters as you're going from start to finish, you're covering the same distance over the same amount of time. We call this constant rate of change. Car travels from one place to another, distance 150 km in 2 hours, assuming the car will travel at constant speed, draw a distance time graph, calculate the speed. Alright? So the distance time graph that they've shown you is essentially just going from one place to the other. You're assuming that the first place is at the origin, alright? And then the second place would obviously be 150 km away from the origin, okay? You could have actually said it's 150 going back the opposite direction, but they just said no, it's 150 away from it. And it took 2 hours. Right? Traveling at a constant speed means that this doesn't change. It's not going up and then stopping and then continuing anything like that. No, it's just a constant speed all the way through. Right? Like I said, what does it mean by terms of the constant rate of change? How far did it travel divided by how long did it take? Right? And this one is done in minutes as opposed to hours. Right? Normally it would be an hour, so it would be 75 kilometers per hour, which is the units that we're used to using in Australia. Right? This one just asks you to work it out in terms of minutes. So just be careful what the question says. It doesn't ask you for in terms of hours or minutes. You just simply divide by the appropriate number to get the answer. Okay? And this one, it's constant because it's traveling at the same rate. Right? So the mathematical term is the same rate. The common term, or the one that we use in everyday life or in physics, is the same speed all the way through for the entire 2 hours. That just shows you the motion of 3 vehicles that actually cover the same distance because they all travel the 2000 to the 2000 mark, but they take different times to do it. Right? So now you need to try and start thinking in terms of the graphical example, which car actually traveled the fastest? And it's the one that did it in the shortest time. So even though they traveled the same distance, car Y traveled the fastest because it got there first. And it took the least time to do so, then car X, then car Z. You can also think of it as the gradient, because that's actually what we're going to be doing, right? The one with the highest gradient, or the steepest gradient, is the one that's traveling the fastest, right? So in this case, it would be 2,000 divided by 60, okay? So that's about 33, whatever it is, right? But the next one is 2,000 divided by 120, which would be half as slow as that. The last one would be 2,000 divided by 240, half again. 1. Although relationships can vary and not necessarily follow a straight line, the average can be found simply as a rate of change between 2 points. So the gradient formula that we're familiar with is essentially the same as finding the average rate of change. Right? I'll use this shorthand a lot, okay? And it's also used in year 12. Whenever you see capital R, O, capital C, it means rate of change. Right? Simply the change of one variable with respect to another between 2 points. For a function f of x, average rate of change between these 2 points. Substitute the second point in, minus substitute the first. This is actually the same thing as y2, which is what you get when you substitute the second x value, minus y1, what you get when you substitute the first x value, x2 minus x1. So hopefully that formula is familiar. We should remember that was your m, which is the gradient that you're looking for. Right? So what we're saying is, you might have a chart where it's describing an object or a particle that's moving, and it goes like this, or whatever, but over the course of the distance, you don't care about, well, not for now anyway, what's happened to it along its journey. We're not saying average, all at once is how far did it travel, so from there to there, over how long did it take, which is from there to there, which in terms of mathematics is actually just the gradient between 2 points in a straight line. So that would be your x2, y2, x1, y1, exactly the same as what you're used to using, except now you're just applying it to a more practical example. Okay. 2 very simple examples. So this graph just shows a curve, but if they're asking you for the average rate of change, all they want is the y2, y1 over x2 and x1 between this point and that one. That's it. So it'll be 30 minus 12, 8 divided by 10, which is whatever it is, 0.4. Okay. Then usually for this stuff as well, physics will really be on it, maths less so, but because there's no units there, so it doesn't actually matter what the units are. Okay? You don't need to say meters per second or whatever it is, because it hasn't told you what the units are. The next one, it's the same thing, right? Except that it's applying to a mathematical function now. Find average rate of change from 1 to 5. That means when x is 1 up to when x is 5. So in this case, that's your x1. That's your x2. You need to find your y1 and your y2. Simply substitute them both in to get your y1 and then your y2. Then you use your y2 1 over x2 minus x1 formula. That's it.